if we look at the Earth or any other large object with mass, in fact, for that matter, any small object, it's just that large objects happen to have a much bigger effect, we see these lines that go around that object with mass. These lines are what we call gravitational fields. Is anyone tell me what direction these gravitational fields point? Yep. They point towards the center of whatever is producing the gravitational field. In other words, if we put an object somewhere in that gravitational field, it would experience a force in the direction of the field. In other words, you put an object right here, a little apple right here, the apple is going to fall down towards the Earth. The gravitational field points towards the Earth. What's the difference between a field and a force? The apple right now experiences both a field and a force. If I was to take the apple away, one of those things still exists, but one of them doesn't anymore. Josh, what's the difference between a field and a force? Well, a field can be experienced as well. So you're right, a field is produced, but a field can also be experienced by something. If I was to put that apple back there, that apple is going to experience both a field and a force. If I take that apple away, though, one of those things, either the field or the force, is going to disappear. The other one won't. Yeah. Okay. Okay, how do we define a force? This is the simplest thing, right? This is the definition of the force that you guys learned in grade 6. A force is a... What's a force? Yeah, you do. Can't pass grade 6 science, guys. Push or pull. A force is a push or a pull. In order to have a push or a pull, you need something to be pushed or pulled. Here's the apple up here. Right now, the apple is being pushed or pulled. It experiences a force. If I take the apple away, the apple is no longer being pushed or pulled. But the influence of gravity is still there. Therefore, we're going to say the gravitational field is still there. The object making the gravity doesn't disappear just because I take away the experiencer. That's why we introduced the idea of fields, to describe that notion that gravity is still there, even if there's nothing there to feel it. Now, in order to have a force, you need that field, but you also need something to experience it, the apple or whatever. Yep. No, you can't. That's a good question, but the question was, if you didn't hear it, was, can we just define the field as hypothetically what the force would be at that location? No, the field is not the same value as the force. Okay, the field is like 9.81 meters per second squared. It's like an acceleration. Okay, the acceleration of gravity, 9.81. The gravitational field strength on the surface of the Earth, more or less, 9.81 meters per second squared. The force is measured in newtons, so two completely different values. Okay. Now, we introduced two equations that describe the gravitational field. The first one, G is equal to big G times M over R squared. And the second one, little g, is equal to F over M. G stands, little g that is, stands for the gravitational field strength. And it's going to be measured, as we said, in meters per second squared, same as acceleration due to gravity, or it can be measured in newtons per kilogram. Either one of those works. Big G is 6.67 times 10 to the minus 11. That's the easy one. What does M stand for right here? What's M stand for in that top equation? Mass. Good. Mass of what? Okay. Yeah, it's the mass of the thing that's making the gravity, the mass of the producer, we call it. Now, down here, we've got a mass as well, right? It's another mass. But this isn't the mass of the producer. This is the mass of the experiencer. This is the thing that's feeling the field. So if we go back to our Earth and our apple again for a second, the first mass on the top here would be the mass of the Earth. The second mass on the bottom would be the mass of the apple, right? The mass of the thing that's experiencing it, right? Now, if you have the mass of both, if you have information about both the Earth and the apple, does it matter which one you use? No. If you don't have mass or information about both, let's say the apple isn't there, or it is there, but you just don't know anything about it, then we've got to use the mass of the Earth. Let's say the apple's there. but the Earth is gone, or we don't know anything about the Earth. Okay, there's a field that's caused by it, but we just don't know any information about it. Then we're going to have to use the mass of the apple in the experiencer equation. Two more variables here. What does R stand for? We think of it as a radius usually, right? But it's not necessarily a radius. Could be, but not necessarily. Yes. Well, careful with that, actually. You're almost right. I said yes before you quite finished, actually. R would be the distance from the center of the producer. Rutgers said, would it be the distance from the center of the producer to the center of the experiencer? No, because you don't need to have an experiencer here, right? If you want to find the field strength at this spot right here, we don't need to have an experiencer there. So we're not going to say from the center of the producer to the center of the experiencer. It's from the center of the producer to wherever it is that you're wanting to find the field strength. Whether or not, Rutger, there's an experiencer there. Make sense? Okay, finally, what does F stand for down here? What does F stand for there? Right? Yeah, it's the force that's experienced by the apple, or whatever the case may be. So if you have information about the producer and you don't know if anything's out there, or if there is something out there, what it is, well, then you can't use the experiencer equation because you don't know its mass and you don't know the force of the experiences. But if you do know something about that apple that's out there, its mass, the weight, or the force of gravity that it experiences, then you can use that second equation, G is equal to F over M. Again, if you know something about the producer, use the first one. If you know something about the experiencer, use the second one. If you know something about both the producer and the experiencer, then pick one. My suggestion in that case would be use the second equation because it's easier than the first equation. It doesn't really matter though. All right, we had a couple of questions for homework last night on page 223 questions, I guess it was. On page 220. Any issues with any of those three questions, please, on 220? Yep. 3, yep. 2B. We're going to do 2B and not to be. This is 3A, so it's not to be. Should we do 2B or not to be, or should we do 2A, 2B, and not to be? That is the question. It really is. That sounds insightful. You know, we should write about that. Like maybe write a book or something, write a play or something like that about it. Sounds really insightful. To be or not to be? That is the question. All right. Number 2B. Compared to Earth, how much stronger would your bones need to be on Jupiter? Well, let's get the gravitational field strength on Jupiter and the gravitational field strength on Earth. Jupiter, the field strength is equal to G times M over R squared. This is 6.67 times 10 to the minus 11 times the mass of Jupiter. On table 4.1 on 218, we should get the mass of Jupiter. What is it? Somebody's got to have that written down. 1.90 times 10 to the 27. Thank you. And the radius of Jupiter, in other words, from the center of the planet to the equatorial, the surface of the equator, is what? Times 10 to the, thank you. And we're going to square that, right? We get a gravitational field strength of what? I'm going to guess about 25. Is it somewhere in the range of 25 when we do this math? Okay. Anybody find that? Okay, let's find it then. Let's do it on a calculator here. I'm thinking that's going to be somewhere in the range of 25. Let's go 6.67 times 10 to the minus 11. Let's multiply that by 1.9 times 10 to the 27. And let's divide that by, use some brackets here, 7.15 times 10 to the 7. Now let's square that. You get 24.789 meters per second squared, or newtons per kilogram works just fine as well. Let's do the same thing for the Earth. For the Earth, we're going to say gm over r squared again. When we do that math, we're going to get somewhere in the range of 9.81 meters per second squared. It might not be exactly 9.81. You should actually calculate that. We're going to do it in the same way as we've calculated the gravitational field strength caused by Jupiter. I just don't want to go through that process right now. Okay, go through the same process. You're going to get somewhere in the range of 9.81. Do you think your skeleton could support your weight on Jupiter? Well, for a brief time, yes, it could. But long term, no, it couldn't. Why not? Because the field strength on Jupiter is 2.5 times the field strength on Earth. How much stronger would your skeleton need to be? Compared to, you guys remember one day we talked about that? If you're trying to compare two things, what do? Divide one over the other. So we're going to say 24.789 divided by 9.81. We end up getting a value of 2.53. So my skeleton would have to be 2.53 times stronger on Jupiter in order to survive long term on Jupiter versus the Earth. Right? Make sense? You want to compare two numbers? Let's divide them. Now, who was it? Travis said, no. Somebody said he did forces. Who was that? Yeah, Josh? Josh said he did forces. So Josh, what mass did you use for the, okay. Now, as long as you use the same mass for both planets, then that's fine, right? Now, you're going to get the exact same answer if you divide two forces. As long as you use the same experiencer, then you're going to get the same number as if you divide two fields. So it doesn't matter, whichever way works. You did get it? Yeah. Okay, number 3 says, what is the magnitude of the gravitational field strength at the equator of Uranus's surface? Compared to Earth, how would your weight change on Uranus? Field strength on the equator. We're going to do this the same way, right? Except this time, it's not going to be the field strength on Jupiter. We're not going to use the information about Jupiter. It's going to be the information about Uranus. So it's going to be 6.67 times 10 to the minus 11 times the mass of Uranus. 8.68 times 10 to the 25 kilograms. And what's the radius of Uranus? It's even better, doesn't it? What's the radius of Uranus? 2.56 times 10 to the 7 squared. That's a big radius. Let's do the math there. When we do, we should get 8.83. They've got the units measured in newtons per kilogram. We could write it in meters per second squared. It doesn't really matter. It's the same thing. Now, compared to Earth, how would your weight change there? Well, we can do this in two ways. Okay, same two ways as question 2b. We can say 8.83 divided by 9.81, because that's what it is on Earth. We're going to get 0.903. Or we can do it the way that Josh did it and find a force. He just made up a mass, basically, of the experiencer, used the same mass, right, for Earth and for Uranus. And when he divided those two forces, he still would have gotten 0.903. Okay? Any issues with that? You guys feel good about that? I'm going to give you a word of caution right now. On your unit test coming up on what day? Wednesday. On your unit test coming up on Wednesday, you will get a question involving gravitational fields. Okay. Now, in the past, I've given a question, not going to say whether I'm giving you this exact same question or not, but I'm telling you I will give you one on fields. If it's the same question that I've given in the past, there's a thing that you've got to be really, really careful about. In that question in the past, I've given both the mass of the producer and the mass of the experiencer, and I've given the distance from the producer to the experiencer. And we would have been trying to find the field strength, G. Now, what did people do? In the past, what have people done for that question? You want to find the field strength there? Well, we've got two equations that are valid. Gm over r squared, G or G is equal to F over M. What do you think people tried to do, though? Well, some did, but most people that made a mistake, and this was probably about 30 or 40% of the class that made this mistake, just said, oh, I got both masses. What do I got to do with both masses? G M1, M2 over R squared. Could you do that? Sure, but you're not solving for what you're looking for. If you're looking for the field strength, what have you just solved for? You just solve for the force. That's not what you're looking for, okay? If you're asked for the field strength, then make sure you solve for the field strength. Okay. Now, there were some people that did this, solve for the force, and then went and did this. Would that be okay? Yeah, if they use that force in here, that would be okay, because the force they found is a valid force. It's just not what you're looking for. So the two options in that question, you could use this one to solve for field strength right away, or you could use this one to solve for force and then divide it by the mass of the experiencer and get the same answer. Yep.
Which seems like a lot of extra work.
It is definitely extra work, yeah. I'm sorry? It is, yeah. Remember I said when we introduced this equation, these two equations, if we set them equal to each other, what do we end up getting? This one, right? Last thing that we do this unit. Talk about a satellite today. What's a satellite? Well, it's anything that revolves around something else. The moon is a satellite of the Earth. We call that a natural satellite. The International Space Station revolves around the Earth as well. It's an artificial satellite. So we've got natural satellites, we've got artificial satellites. Both of them revolve around something else. We have in our school division, it's kind of an alternative school called St. Luke's. It's for people that just, the regular school setting just doesn't work very well. It started in Okotoks. We now have what we call satellite schools. Okay, satellite campuses in Brooks and in High River. Okay, satellite campuses are these campuses that are around, kind of revolve around that main campus in Okotoks here. A satellite is anything that revolves around something else. A natural satellite occurs in nature, like, for instance, the moon revolving around the Earth. Just because it's natural, like the Earth revolving around the sun or the moon revolving around the Earth, doesn't mean it's not a satellite. It still revolves around something else. We just call it a natural satellite versus an artificial satellite, which doesn't occur naturally. It could be the International Space Station revolving around the Earth. It could be something as simple as a car going around the middle of the car going around a circle around a racetrack. Okay, a satellite is something that revolves around something else. Okay, if it's not natural, then it's got to be artificial. Record question? I'm sorry? Absolutely, yes. The question, if you didn't hear it, was, by that definition, would the Earth be a satellite of the sun? The answer is absolutely yes. The Earth is a satellite of the sun. We don't usually think of it that way, Rucker, but it is. To be honest, we usually think about satellites as being artificial things, right? That's kind of the popular connotation to it. Right? It's a communications satellite, it's a spy satellite, it's a space station, whatever. But in the end, the Earth going around the sun, the moon going around the Earth, just as much satellite as a spy satellite going around the Earth. Let's just take a peek at this link that we see right here, which, by the way, you could look at as well. You could go to this spot as well. All you have to do is Google ISS sightings Calgary or ISS sightings Okotoks, and it'll take you to this website. This is a NASA website. You can type in any city you want in the world. Calgary. If you type in Okotoks, it'll just give you the results for Calgary. It tells you when the International Space Station is visible over top of Calgary and Okotoks, and it's visible all the time. I shouldn't say all the time, but it makes, I can't remember how many orbits around Earth that it makes per day. Depends upon the flight path. It's often visible right above us. Okay? How many people have ever seen it? You look up and see this bright thing in the sky going across the sky fairly quickly. Tell it's not an airplane. It's farther away than an airplane, but you can tell that it's not, a shooting star either. Who's seen it?
I think I have.
Think you have? Okay. If you haven't seen it, you should check it out. Seriously, it's kind of neat to sit down here on your back deck or go out in the country and see this thing going above and know that there's people on that. Like there's people on that are just floating around in there. And it's kind of neat. Anyways, next time it's visible in Okotoks is tomorrow. But it's not a very good sighting. It's only visible for 1 minute, and it's only visible 14 degrees above the horizon. In order to have a good sighting, we want to have 30, 40, 50 degrees above the horizon. So I would say the next really good sighting that we'd see, it's too bad. This one's a 4-minute sighting, so it lasts for a while, but it's only 23 degrees above the horizon here. I would say probably the next real good sighting, this would be the one coming up that I'd watch out for. Sunday, December 15th at 5:57 p.m. So it's a good time of day as well. Okay, it's just after supper. 4 minutes, 44 degrees. You want to see it? 21 degrees above the southwest. So we're going to look down that way. Okay, it's going to appear in the sky there, and then it's going to disappear above the east. So it's going to go like this, 22 degrees above the southwest. It's going to go up in the sky like this, and then it's going to come back down to the east, and you're going to see it all the way across the sky for 4 minutes. Again, sometimes it appears for less than a minute. Sometimes it appears for 5 minutes. If the sky is clear, you will see it, and you won't mistake it. You'll know exactly what you're seeing when you see it. It's a bright thing. It's a bright light, and it's usually the brightest light in the sky. And it's going across the sky fairly fast. And again, you're going to know that it's not an airplane, it's too far away, but you're also going to know that it's not a shooting star. Now, when we talk about satellites, we're usually talking about satellites in the sky, like the space station, or like the moon orbiting around the Earth, or like the sun, the Earth revolving around the sun. What holds the Earth in orbit around the sun, or what holds the moon in orbit around the Earth, or what holds the International Space Station in orbit around the Earth? Well, it's a centripetal force. But the centripetal force, as you know, has to be caused by something. It's not a force on its own. It always has to be caused by something. What's it caused by in this case? What's pulling the Earth in towards the sun? What's pulling the moon in towards the Earth? What's pulling the space station or a spy satellite in towards the Earth? We've been talking about it now for a couple of weeks. It's gravity. There's a centripetal force that's caused by a gravitational force. In other words, an mv squared over r force that's caused by a gm1 m2 over r squared force. Travis? Yes, they are. That's a good question. Travis just said, aren't they falling? Aren't satellites falling? Yes, all the time, constantly. That's the reason why the astronauts on the space station appear to be weightless. They're not weightless. The gravitational field strength 400 kilometers above the Earth, they're not actually that far away. When they're going above us, they're as close to us as my mother-in-law in Edmonton. Literally. It's just a lot easier to get to Edmonton than it is to get to the space station. As those astronauts orbit around us at a height of 400 kilometers above the Earth, they are constantly falling, free falling towards the Earth, and that's why they appear weightless. As they fall towards the Earth, the normal force is zero, and there is no normal force. There's still a force of gravity. It's about 90% or so of what it is on Earth. They just don't perceive that force. They just don't feel that force because there's no normal force. They're falling, but moving at the same time. So they want to go off in a straight line, but they don't go off in a straight line because gravity pulls them down. So instead of going out, or instead of going straight down, where do they end up going? This way, and then this way, and then this way, and then this way. As they constantly fall, they fall around the Earth. It's like being on the space shot that you guys were on at West Edmonton Mall here a couple weeks ago for 6 months, falling straight down, free falling straight down for 6 months, as opposed to for 3 seconds like you did. Your stomach would kind of adapt to it over time, though. Good? So how do we analyze this then? Well, we said that there's always a centripetal force, and that centripetal force is mv squared over r, but that centripetal force is always caused by some other force, like gravity, which in this case would be equal to the centripetal force. We've done problems where centripetal force is equal to friction. Centripetal force is equal to the normal force plus gravity. Here, the centripetal force, Fc, is just equal to the gravitational force for Fg, right, Travis? Centripetal force is mv squared over r. The gravitational force is g m1 m2 over r squared. Now it gets a tiny bit tricky here. R appears on both sides. It means we can cancel one of them out. If we multiply both sides by r, the r disappears on the left, and one of the r's disappears on the right. So it becomes mv squared equals gm1 m2 over r. Now what about these masses? M1 would stand for the mass of the producer. We'll say it's the mass of the sun if it's the Earth going around the sun. We'll say it's the mass of the Earth if it's the moon going around the Earth, or it's the mass of the Earth if it's a space station going around the Earth. ME, we'll say, is the mass of the experiencer. What mass is it over here on the left side? Producer, experiencer. What mass do we use when we're talking about centripetal force, an object going around in a circle, mv squared over r? What mass do we use? The producer that's in the middle of the circle, or the experiencer that's actually going in the circle? Which one is it? See, do you have any idea on that one? Okay, the one that's going around the circle, which is it would be the experiencer in this case. Yeah. If we've got ME on both sides, then that cancels as well. So now we're left with V squared is equal to G times M, the mass of the producer, over R. Typically, what we'll do at this point is rearrange this to solve for V, so that we can solve for the speed of that satellite. Yep, yeah, just square root it. If we're solving for V, that is. I'm going to leave it as V squared over R there is equal to GM over R. Sorry, V squared is equal to GM over R, because you'll often solve for another variable. But if you are solving for V, you're just going to square root it, GM over R, square root. All right, we got a couple problems we're going to work on for practice questions here, or example questions. The first one is 5.11 on 278. It says the Earth's moon is 3.844 times 10 to the 5 kilometers from the Earth. We'll assume that's from the center of the moon to the center of the Earth. What's the orbital speed of the moon? We're going to say every time we're dealing with a satellite problem, Fc is equal to Fg, or mv squared over r is equal to gm1 m2 over r squared. We'll cancel out one of the r's. We'll cancel out one of the m's. V ends up being equal to the square root of g times m over r. We're going to derive that equation every time we do a question like this, because this equation isn't on our data sheet. F is equal to mv squared over r is. F is equal to gm1 m2 over r squared is, but the combination of them is not. So we're going to derive it every time just so that we remember how to do that on the test. What m do we use here, the mass of the producer or the experiencer? No. It's actually the mass of the producer. Because remember the mass of the experiencer? Canceled? We're left with the mass of the producer. So in other words, it doesn't matter how heavy the moon is, it's going to orbit around at the same speed. Anybody want to make a prediction as to what the speed is going to be, how fast the moon is moving? 6.67 times 10 to the minus 11. The mass of the Earth is 5.97 times 10 to the 27, and that's on that table. It's also on your data sheet. R is 3.844 times 10 to the 5. Is that right? No. Yeah, really? Yeah, good. Convert it to meters. It's 3.844 times 10 to the 8 meters. Now, we don't have to square that because one of the r's canceled there. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 27. Anybody make a guess for this speed here before I calculate this? Fast or slow? Fast? Okay, let's square root that. And we get 32,000 meters per second. 32,000 meters per second. That was actually 3 digits, so it actually should be 3.22. 32,000 meters per second. That's fast. For perspective, the speed of sound is 3 times 10 to the 2 meters per second, as opposed to 3 times 10 to the 4 meters per second. This is moving. The moon is moving at about Mach 100 as it goes around the Earth. Okay, about 100 times the speed of sound as it goes around the Earth. Why don't you hear a sonic boom? Why don't you hear that boom as it goes by? You got to have air to hear a sonic boom. Okay, you got to have sound waves set up in air, and where the moon is orbiting around the Earth, there is no air. So it doesn't matter how fast it's going. There's never going to be a sonic boom. Okay? All right, let's see what you can do with these two questions, please. Let's take a look at question number 2 up here, please. The moon Miranda orbits Uranus at a speed of 6.68 times 10 to the 3 meters per second. Use this speed and the mass of Uranus to determine the radius of Miranda's orbit. The mass is Uranus is 8.68 times 10 to the 25. We want to find the radius of orbit. We know that for both of these questions, FC is equal to FG because it's a satellite. Anytime we have a satellite, we can do this. MV squared over R is equal to G M1 M2 over R squared. One of the R's disappears. One of the M's disappears. We're left with V squared is equal to G times M over R. What M is left here? The mass of the producer, the mass of the experiencer. Which one's left? Which one canceled? Okay, we had an ME right here and an ME right here. The mass of the experiencer canceled. That leaves us with the mass of the producer left. So we don't care about the mass of this moon, Miranda. We care about the mass of the producer, which is the planet Uranus here. We're solving, though, for R. Let's rearrange this to solve for R. The R goes up by multiplying, and the V squared goes down by dividing. So it becomes G times the mass of the producer over V squared. That's 6.67 times 10 to the minus 11 times the mass of the producer, which is Uranus, 8.68 times 10 to the 25. Divided by the speed, which is 6.68 times 10 to the 3. And we got to square that. So do the math there, and it should work out, I think, to be 1.30 times 10 to the 8 meters. Is that good? Okay, I got 2 more examples that I want to do with you. First one is 5.121.279. So it says Landsat is an Earth imaging satellite that takes pictures of the Earth's ozone layer and geological features. It orbits Earth at a height of 912 kilometers, so about twice the height of the International Space Station, a little bit more than twice the height of the ISS. What are its orbital speed and period? All right, the speed sounds like it should be an easy thing to find because we've done that before. The period, maybe not so much so. We know that FC, again, is equal to FG. We're going to derive this equation each and every time because we want to get in the habit of being able to do it. R's cancel. One of the M's cancel. I'm left with V squared is equal to G times M over R. What mass am I left with? Mass of the producer, mass of the experiencer. You guys got to know this by now, right? It's the mass of the producer. We want to solve for speed. Let's go G times the mass of the producer over R, and let's square root that. 6.67 times 10 to the minus 11 times the mass of the producer, which in this case is the Earth. 5.97 times 10 to the 27, 10 to the 24. Where do we get that number from, by the way? 5.97 times 10 to the 24. It's in your textbook and it's on your data sheet, right? And we're talking about a distance of 912 kilometers above the surface. What do we use for R there? 912? 912,000? Neither one. What's the value of R? Yep. Yeah. Why do we add those two numbers together? First of all, where do we get the 6.38 from? Where did that number come from? Yep. It's the radius of the Earth, and it's on our data sheet. It's also in your textbook. Why did we have to add those two together, Lane? Good. Good. If we're 912 above the surface, we want the distance from where the satellite is to the center of the Earth. We have to add the radius of the Earth to however far it is above the surface. So add those together, and then we do our math there. Okay, let's pull up the calculator again. Let's say we've got 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Let's divide that by, let's use some brackets here because we've got to add some numbers before we square it. 6.38 times 10 to the 6 plus 9.12 or 912,000. Let's square that bottom number. We end up with 7.4887. That doesn't sound right. Anybody else get that? Oh, you don't square the bottom one. That's right. The square disappeared right when we canceled it. So, can I scroll up there? Okay, when we fix that, we squared the bottom. We shouldn't have squared the bottom. We end up getting 7,000, Wilson, 7,000? 389 meters per second, which is a lot better, right? 7,000 meters per second versus 7 meters per second for a satellite orbiting the Earth is much, much better. Okay, 7,389 meters per second, which if we round it to 3 digits, it would be 7.39 times 10 to the 3 meters per second. Now, you want to find the period? This is easy, actually. 2 pi r over t. We're just going to say t is equal to 2 pi r over v. We know the value for v. We just found it. The value for r, that's 6.38 times 10 to the 6 plus 912,000. Do your math there, and you're going to get an orbital period in seconds. Okay, if you did this for the Earth, you get the orbital period for the Earth revolving around the Sun, okay, which would be equivalent to about 365 days. Yep. Fraser? It would be relative to the Earth, yes. That's a good question, though. Yes. It's all relative, right? Every speed we've ever calculated is relative to something. Because, cars traveling down the road at 100 kilometers per hour. Relative to what? Relative to the ground or relative to another car? Well, relative to the ground, right? Relative to the Earth's ground or relative to the ground on Mars, right? It's all relative to something. We usually assume relative to the Earth. Hey, but Fraser, in a context like this, when you're talking about space, it probably is a good idea to state that. Even though that's the general assumption, it's probably a good idea to say that it's relative to the Earth. Yeah. Relative to something else in space, it could be at rest, possibly, right? Or it could be even moving faster. Okay, try these ones. All right, let's take a look at one more example here. This is called a geosynchronous satellite. Geo means what? Geo means Earth. Synchronous means it's synchronized with Earth. It means a geosynchronous satellite means that it maintains its same position above the Earth at all times. This is important for some satellites, not for all of them. If you got a spy satellite, then you don't want it necessarily to maintain the same position above the Earth. You want it to move around. You want to one day be taking pictures of North Korea, and the next day be taking pictures of Iran, and the next day taking pictures of somewhere else. So you don't want it to maintain the same position. But if you got a communications satellite, you want it to be geosynchronous. You want it to maintain the same position above the Earth same place above the Earth, because if it doesn't, you're not going to know where to find it when you want to communicate. Okay. For instance, the satellite that broadcasts your TV signal. How many people have satellite TV here? Okay, the satellite that broadcasts your TV signal. You've got a little satellite dish that's aimed up in the sky. It's not aimed at a random spot. It's aimed at that geosynchronous satellite that's up in the sky. Okay, you need your satellite receiver to know where to look. So in other words, if the satellite is moving around relative to where you are, you don't want to get a TV signal only when it's passing above you. You want to get it all the time. You need it to maintain the same position. All right, we want to find the height at which above the surface that the satellite has to be placed in order to make it geosynchronous. For all geosynchronous satellites, it's the same height. They're going to be in different spots depending upon where you want to communicate from, but they're all going to be the same height. Let's say FC is equal to FG. That's what we do for all satellites, right? MV squared over R is equal to GM1 M2 over R squared. One of the R's cancels. One of the M's cancels. We're left with V squared is equal to G times the mass of the producer over R. Now, we want to find the height above the Earth, not the distance from the center of the Earth. But first, we've got to find R to do that. R becomes equal to G times the mass of the producer over V squared. We know what G is. G is 6.67 times 10 to the minus 11. We know what the mass of the producer is. It's the mass of the Earth. Do we know what V is? Hold on for 2 seconds here, guys. Do we know what V is? How fast does this satellite have to be going? We don't know. Just pay really close attention here, okay, until I finish this up. We can figure it out. It's 2 pi r over t. So let's replace that. Let's get rid of these numbers for a second. Let's replace that V with an expression. Gm over 2 pi r over t squared. Looks ugly. It is ugly. G times M time divided by, let's square everything inside the brackets now, 4 pi squared r squared over t squared. Squared everything inside the brackets. Now what I'm going to do is take this entire term up by multiplying. It becomes 4 times pi squared times r squared times r over t squared. R squared times r is r cubed. 4 pi squared r cubed over t squared equals gm. You guys remember Kepler's third law? T squared over r cubed. T squared r cubed. We want to solve for r here. Now, how do you get r? Oh my goodness. You got to take the cube root of it. You guys ever done that? The cube root of a number? It's not the square root, it's the cube root. So it becomes the cube root of gm over t squared over 4 pi. Now, that distance is going to give us the distance from the center of the planet, the center of Earth, not from the surface. What's t? What's the period? If it maintains the same position above the Earth, and the Earth makes one rotation on its axis in 24 hours, then how long does it take the satellite to go around the Earth? 24 hours, which we got to convert to seconds. So get r, that's the distance from the center, then let's subtract the radius of the Earth from that. I want you to do 2 things for homework, guys. Finish up those questions right here on page 279, and do your best to solve this. You've got the equation written down already. Try to solve that equation that we've just written down. Do your best to do that, okay? Get that done for tomorrow, and then we'll see if we can take a look at it first thing tomorrow. All right, have a good night, everyone.